So this is going to be a bit of a high-level talk at the beginning, and then I'm a technical person, so I can't resist showing you some details in the middle and the end. I thought I'd start by just reviewing the definition of trust. So I looked it up in the OED, and trust is defined to be the firm belief in the reliability, truth, or ability of someone, something, or confidence or faith in a person, thing, or attribute. So probably most of you, if you've thought about trust in the context of computer science, maybe the first work you saw was Ken Thompson's famous Turing Award speech, where he reflects that he got the award for Unix, but he used his speech to talk about a sort of pessimistic view of computer systems at the time. And for those of you who haven't seen the paper, the problem he looks at is of Trojans. So he considers a kind of attack where someone compromises a compiler by changing the behavior of the compiler on some inputs. And so although even you might have done a lot of work to make sure that the program you wrote was the one you wanted, the compiler spits out a program that does something else. And then even worse, if you consider about how compilers are built, they're typically built by bootstrapping and so on. He argues that basically no amount of source level verification or scrutiny can protect you from relying on untrusted code, whether it's in the compiler or even somewhere lower level down the stack. So this is kind of a depressing view. And if you start to think in an adversarial manner about our computer systems, you very quickly get depressed. But there's another community that's been working on techniques for building trustworthy software. And over the last few decades, they've had some successes and found ways not to completely eliminate the need to trust some parts of our systems, but at least to reduce or locate trust somewhere else. And so to take the problem that Thompson was concerned with, he was worried about we can't trust our compilers, and therefore, we don't know that the output of the compiler does what we want. There's some beautiful work. This was actually invented in a thesis in the 70s, but it was made famous by Amir Pinelli and his colleagues. Amir was a formal methods researcher. And they discovered this idea called translation validation, where by building a small shim around the compiler that just encodes the meaning of the input program and the output program, you can have the middle of the compiler do whatever it wants. It can do crazy optimizations. It can do, use exotic algorithms for doing things like allocating registers or transforming your code. It doesn't really matter because you have this kind of before and after view of your program, and then you can build a proof that those things are the same. And so to gain assurance that this program compiled to this output, all you need to do is check that proof. And in practice, because logic is sort of simple and highly mechanical, you can engineer a really small proof checker that can check the validity of these proofs. And so this is a way to take, I haven't drawn it to scale, but a compiler is a large, complicated program. But the parts of the compiler that just encode the semantics of the input and output are small, and the proof checker is much smaller than the compiler. So this can give you a way to gain assurance about at least particular runs of the program. So this is a way that we can sort of find our way out of parts of the mess that Thompson pointed out. So if we turn to networks, the situation's bad. And I didn't pull up today's headlines, but there's lots of ink being spilled about 5G and backdoors, and in general, people are realizing that the network infrastructure is a thing that's kind of Swiss cheese if you look at it from a security perspective. A friend of mine recently told me about this article that I was not aware of. It's a really fun read if you get a chance. It's called The Athens Affair. It's an IEEE Spectrum, and it's about an attack on the cell phone network in Greece around the Olympics, where basically the communications of many, many high-level people, including politicians and so on, were intercepted, and the attack itself was pretty sophisticated and interesting, hooking in at quite low levels of the telephone infrastructure. So again, you might be depressed and think, well, this is pretty hopeless. Most of you are involved in building the systems that run in networks, and you know how complicated they are at all levels. And so you might think that this is not, that we can't trust our network systems. But I think there's reason to have hope. I think P4 gives us, much like the translation validation idea, it gives us a way to think about some abstractions and to build tools based on logic and formal methods at that level that we can then use to start building a foundation for trustworthy networks. Now, you might say, isn't P4 too simple? And you'd be right. I think Andy, as someone has pointed this out many, many times, if you take, say, just a single router or switch, it might have, let's say, order 10,000 lines of, say, P4 or data plane level code, and it probably has several 100,000 lines or millions of lines of code between the operating system and the control plane and everything running on top of that. So it's true that the data plane is sort of just the tip of the iceberg. But as I showed this morning, P4 is also sitting in this really interesting part of the stack. I like to think of it as the contract between the control plane and the data plane. And so from looking at sort of problems about how we can reason about whether the network is doing what we want, you can ask the question sort of from above and below. And viewed from above, P4 gives us this fairly high level, fairly declarative and simple and tractable statement of how each device in the network processes packets. And so if we can have ways to build trustworthy implementations of that abstraction and then reason about them, we can use this as a building block either to do things like translation validation of control planes or start building verified systems higher up the stack. And then looking down, of course, if you're on, say, an FPGA or a programmable ASIC, you can also sort of take the other view and view the program as taking instructions about how to process packets. And so you could also imagine taking that as sort of your specification and moving down further and doing things like building verified compilers and even synthesizing verified hardware, which is a thing that people are doing now. So I think, although this iceberg picture is totally true, P4 is kind of in this sweet spot, and it's an excellent vehicle for doing formal methods work applied to networks, and so we can use it as a way to think about regaining trust. So I want to tell you about two pieces of work, one that sort of looks down and one that sort of looks up, and just give you a taste of what this work looks like. So first I want to talk a bit about data plane verification. This is something that has become a bit of a hot topic in the academic community. There's also efforts in various startups and in industry to do it. And I think the people who get credit for sort of resurrecting it most recently are Brighton Godfrey and his group at UIUC, and Nick and his student Payman, who at the same time sort of realized that SDN and OpenFlow gave you suddenly the ability to have this simple artifact that described forwarding behavior, and you could start to build logical models and reason about it. So over about 5 or 6 years, this area has gotten more and more sophisticated. And I just want to show you a piece of what you can do today. So this is a system called P4V that we built a couple years ago, and it was published at SIGCOMM last year. And just here's a little demo of it running. This is a toy example, which you can't see. Let's see. Let me just quickly mirror my screen. Sorry about that. OK, great. So this is just a toy example. I actually stole this from Payman because it's one of the examples that his company, Forward Networks, discovered and then wrote about in their blog. And the thing I want to show you is just there's a full P4 program here. There's a parser. It's got some headers. It's got some tables. And these tables do network address translation and access control. And the point is not so much the details, but just that we can write down properties that we expect this program to have, like we might assert that packets from a certain IP address are going to be dropped. And we can, in pretty much a fully automated way, run this and discover that it actually doesn't have the property we want. We get a counterexample that tells us what went wrong. In this case, the problem is that our access control list missed. And if we go back, we realize that, oh, maybe we applied these tables in the wrong order. So we first translated addresses and then tried to filter them, but we were filtering the original addresses, not the translated ones. And so if we switch this around, so we do the filtering first, now suddenly our property holds. So again, this is not going to solve the Greek politicians having their phones tapped, but it just shows you that we can start to efficiently and automatically check properties of the data plane, and that's a powerful primitive we could use to do other things. So how does this work? Well, Kone and Stefan this morning talked about using P4 to do validation of fixed function chips, and it's really the same idea. P4 being this relatively simple language that doesn't have complex data types, doesn't have loops, is very amenable to formal reasoning. So the tool we built basically translates P4 programs into a simple imperative representation, sort of much like C, and then uses some classical ideas from program verification to turn this into a logical formula, and then passes it off to a SAT solver, and then you get push-button verification. And lots of other people have done this. Andy and his collaborators have done it, Kostin Regu at Bucharest, and several other teams as well. So how does this work? Well, for the most part, it's basically viewing the P4 program as just an ordinary program, converting it to logic. But there is one interesting sort of wrinkle, which is that the P4 program is only half the program. So it only specifies the data plane behavior, but it doesn't tell you how the control plane is going to behave, and in particular, what's going to go into the tables. And so from a logical perspective, what this means is that any table in your program could do anything. It could miss, it could hit, it could apply any of the actions. And if you want to reason about many data plane properties, you need some way to know a bit more about what the control plane is going to do. So in P4V, what we did is we just sort of continued down this path of viewing P4 programs as just ordinary C-like programs, and we added some extra state. So in the front end of our tool, we instrument the program with extra bits that capture all the different non-deterministic decisions that could be made from the data plane perspective, or if you want, all the different configurations that the control plane could make. This is showing the instrumentation of one table. So we start out with just this single table being applied to this statement, and we have some state that's been added at the top of our program that tells us, was this table reached, did this table hit, and then which of the actions was run. And the actual expansion of the table in our tool looks like this. So it becomes a kind of big mess of code that handles all the possible cases, and then records in this extra state what happened. And now, if we want to capture some property of the control plane, for example, maybe we know that a certain IP address is going to be filtered in the ACL list, we can turn this into just a corresponding assertion on this extra state we've had, and now we've sort of fused the control plane properties with the data plane properties, and we can continue verifying. Okay, so that's all I'm going to say about data plane verification, but I think there's, again, just the opportunity here is that P4 is simple and tractable, and so a lot of the things that would bog you down if you were trying to verify C++ programs or other things just don't apply. So what about that other way? What about looking up at the control plane? And here, I don't have any P4 specific work that we've done yet. I have a direction that my group is going, but I wanted to tell you a bit about some work we did 5 years ago looking at this problem in the context of OpenFlow. So kind of turn back your clock and pretend that it's 2012 and we're sitting here at one of the early ONSs instead of at the 2019 P4 workshop. If you recall, we're considering a sort of model like this where there's a logically centralized controller, it's got some program, and it's reprogramming a bunch of fairly simple OpenFlow switches in order to implement some set of paths. And I'll just give you an example of the kind of problem that can arise when you do this. This is something that we realized by looking at the spec and then running some code, I think, on some early PK8 switches. And we realized that your control program could sort of think that it was stepping the network through a series of states. In this case, I've shown the state sort of around the top of this box. And what's meant to hold is that we're always going to filter certain traffic, say some SSH traffic. And so we're careful to first install that rule and then install rules that actually do forwarding. But if you read the OpenFlow spec carefully, it said that, well, switches were allowed to reorder the messages they got from the controller. And so what could actually happen is that you step through this other series of states where you first installed the forwarding rules and then finally got around to installing the filtering rules. And so the states I've shown in red are actually not correct states from the point of view of this property. We're allowed to send packets to the network that really shouldn't be allowed. And again, this might seem like a toy example, but if you think about this happening in a public cloud or in a situation where these rules are being applied specifically to enforce some security policy like keeping some parts of the network isolated, it's a problem, even if this is a transient error that eventually goes away. So the solution is OpenFlow provided some barrier primitives you could use to synchronize the controller's view of the network state with the switch's view of the network state. So it's not a hard fix, but it's something that's not obvious if you're just sort of casually writing controllers. So the way that we solved this problem was actually a bit more methodical and and expansive. So we actually took the OpenFlow spec. This is OpenFlow 1.0. It was a nicely written English document with lots of prose and diagrams and C structs that define the various message types. And we turned it into a formal calculus that we called featherweight OpenFlow. This is sort of a selected set of syntax from the calculus. So we had sort of programs that represented controllers and links and switches and tables. And then we had, most interestingly, an operational semantics that says exactly how the entire network processes packets. And because networks have a lot of concurrency, we had to use some slightly fancy ideas from the programming languages literature. So we borrowed this idea of the chemical abstract machine, which is something that some French process algebra people invented about 30 years ago. And the intuition is that concurrent systems are kind of like chemical solutions. They kind of have lots of different threads or molecules that are just interacting with each other. And so you can model concurrent computation that way. And so in our setting, we took the OpenFlow network and we modeled it in this chemical abstract machine way. So we had molecules for the controller, molecules for all the links, molecules for all the switches. And the overall network was sort of the big concurrent composition of all these pieces. And then the semantics of the network was given by a sort of non-deterministic step function that said how every individual step of computation works. Just to show you a little piece of this, here's how we would model things like the controller reprogramming a switch. So a controller could have sent a message to a switch. It's sitting on the link between the controller and the switch could then incorporate that rule into its buffer. So that would be one step. And I'm not going to show you the details, but later on, the switch could take the message out of the buffer and actually reprogram its flow table to work differently. So you see that there's no ordering implied here. So the buffer that the switch has is really a set. And so the messages could get reordered depending on how it chooses to pull things out of the set. So a barrier request, by contrast, that comes from the controller, really it forces the switch to process all of its messages. And so this rule says that a switch can only go past a barrier when it's already processed all outstanding messages. So this is how you can avoid that bug that I showed you. And what we were eventually interested in showing was that if your controller is trying to implement something like what's now called intent-based networking, so if it has sort of a model of the paths that the network should implement, something like this, then we want the OpenFlow implementation with a controller to do that. And so what we're really doing is relating this kind of abstract path above with all of the states of the switches in the controller and all their interactions that are happening concurrently. And so we were able to prove this by essentially building a controller stack that started from a high-level intent framework and then systematically mapped it down to a runtime system that would manage the interaction with the switches. And so on the way, we had to prove that our compiler was correct. I won't dwell on this because I'm running short on time, but we proved not only the mapping from kind of a high-level policy language down to OpenFlow tables, but also several optimizations. And then more interestingly, we had to prove that the runtime system that was managing the state of all the controllers and barriers and so on was correct. And for that, we actually found a really clean way to do this that applied not just to the specific controller we were building, but actually to any controller that satisfies a couple of basic invariants. Essentially that these invariants imply that the network state is a subset of the controller's view of the network. So if you can prove that holds at all times and that the network makes progress towards the ideal state, then you can show that the network satisfies this intent-like spec. And we actually proved this in a Theorem Prover. So we did all this in the Coq proof assistant. So we modeled all of these semantics and languages and translations in Coq, and we proved that all of these theorems that I've shown you in typewriter font actually do hold in Coq's theory. And then we were able to extract from this runnable executables that we actually ran in our home networks and in the lab for quite a while. And so, again, I know that went a bit fast, but this sort of shows you how if you start with something like OpenFlow, or nowadays P4, you can use it to build not just correct data plane programs, but even higher level things like controller frameworks or control applications. So looking ahead, I'm really excited about doing the same thing for P4. I hope some of you have seen our poster. We have a new project that we started a few months ago where we're building a formal semantic model of P4. And we're also interested in building things like verified compilers. And just to wrap up, I guess I'm excited about this space because in general, I think language-based techniques are a great way to address problems with trust in all kinds of systems, but especially network systems. I think P4 is a really ideal vehicle for kind of serving as an abstraction. It's quite low level, so it's close to the hardware, but it's also simple and tractable. And there's lots of future work. So formally specifying the language. I think this problem of specifying the interaction between the control plane and the data plane is a really interesting and rich space. And then engineering verified systems like compilers and runtimes is a fun challenge as well. OK, so I'll stop there and take questions. And thank you all for your attention.
Two things, if I may. One is, how do you know that when you specify an action in P4, the actual implementation doesn't take additional actions that are not visible in the P4 that you're analyzing? And the other is, how do you handle externs, which are essentially black boxes and you have no idea what's going on inside?
So there's two questions. I think the first is, how do we know that the hardware or the target is implementing what we're doing? So I think two things. One is, there are people working on how you could map from low-level languages like P4 all the way to hardware. So Adam Chapala's group at MIT, for example, is looking at doing synthesis all the way down to hardware descriptions. So that's one way, if you were being super paranoid, you could do this. And the other way, which I think is a little lighter weight and probably more accessible in the short term, is we can also do runtime verification. So I didn't have time to cover this, but one of the killer apps for P4 is in-band network telemetry. And I think having the ability to collect rich data about, at a fairly low level and sort of ground truth, this is what the router's doing. We can use that to feed into runtime or offline verification that check that weird stuff is not happening. So you can view this, it's not just the implementation of the network, it also gives you this kind of microscope that you can use to zoom in and see what's happening. There's a second question, which I've now. Externs. So in our system, we just model externs as stateful objects that we have to write down descriptions of.
So you've talked a bit about formally specifying P4 and using verification, maybe through Petra, to help pin down what P4 actually is. Are you planning on introducing new concepts to the language to help with that process?
I'm not sure that P4 itself needs much more. So one thing, to give an example, a lot of systems that have done this kind of verification have needed to do so in a compositional way just to make the reasoning scale. But P4 programs are relatively small, and automated solvers, if you're doing automated verification, have gotten really fast. So our experience with verifying large programs like Switch was you don't have to do that kind of decomposition in order to actually analyze the full program. The one thing that I think probably will be needed is right now a P4 program has a control plane interface. That's what P4 runtime gives you. But it's not really written down separately from the program. So you just have to read off, here are my controls, here are my tables, here are my actions. And I think it would be great to have something like an interface that specifies, at first, just like what are the tables and what are their names. And then maybe later on also gives you some ability to specify semantic properties, like these two tables will be programmed together. And I don't know what that language would look like, but you can imagine a separate, standalone, but hopefully simple description of that.
So I think having an executable spec is something we should all aspire to. At least with OpenFlow, we sort of had a reference implementation for a while, but certainly not an executable spec. And I think, I guess my question for you is, are you going to include this executable spec as part of the official P4 specification?
So Petra, we're planning to contribute to p4.org. We're in early days, so we've only really specified large parts of the front end. We're hoping to finish an interpreter, which would serve as sort of a golden reference implementation of the language, and we will contribute that. There are some challenges. So P4 intentionally leaves lots of things up to targets. And so finding ways to model those choices in a clean way. You don't want to allow anything to happen, but you want to say that the architecture of the target gets to make these choices. That's a kind of modeling question that Others, like Peter Sewell's group at Cambridge, has modeled, say, TCP, and finding ways to build, they call them loose specs, that can kind of capture the important parts of TCP but leave room for implementations to make their choices is tricky.
Regarding the Ken Thompson problem, there's this terrible problem with kind of SDN and P4 and agents that you have. All of a sudden, so many more attack vectors. So, for example, you have to trust the P4 agent. You have to trust a controller, which may be very large and many millions of lines of code. And then, of course, they're running on commodity CPUs, which we know have all these kind of information leakage vulnerabilities using DRAM, which is vulnerable to things like rowhammer. What's your thought about, sort of dealing with all these other vulnerabilities that we've unintentionally introduced into our networks?
Great question. So I'm actually inspired by Pinelli's work on translation validation. I think we can find the pieces that give us the ability to either observe or check the properties we want, and then we need to find ways to trust those pieces, but not the whole stack. That's an aspirational statement, but I believe something like that is the way forward.
Okay, last question.
So earlier today we heard that the collaborative development of P4 code was very difficult in this instance of Arista, I think it was. So is this going to help also with having more people work together on a language, on programs?
I hope so, but I'm out of time, and I think Mario's going to talk a bit about that, maybe. So I should probably. So yeah, I think this kind of verification could give you the way to think about programs that are developed independently and then fused together, and the conditions that you need to do that kind of correct composition. It's probably not going to be as clean as, say, composing Java objects. It's going to be something lower level, and there's going to be hairy interdependencies between, the bit level representation of the data and also other properties of these pieces. So I think that form of verification may be needed for that. But I've thought about it less than Mario, so I'll defer the remaining time to the gentleman from New York City to tell us about that. Okay.
Okay, thanks again, Nate, for bringing some order to our world.